Good morning, everyone. This is Hailong Liu from NICE, Japan. Today, I would like to talk about the motion sickness modeling with vision vertical estimation and its application to autonomous personal mobility vehicles, the APMV. This work also has been accepted as a regular paper of this IV 2022. As a background, the autonomous personal mobility vehicle APMV is a mini type of EV with an automated driving system. It's different to the autonomous car because it have a lower speed and lower acceleration. That's why it can be used in some mixed traffic, such as in the shared space, on the sidewalk, in the shopping mall, and in the station. But in those cases, the APMV has a higher opportunity interacting with a pedestrian than the autonomous car, which means the APMV will frequently take the avoidance behaviors for driving safety. However, those frequent avoidance behaviors may make the passenger get the motion sickness. Moreover, if you are reading a book or using a laptop PC for working, or play the game, for example, by Switch on the APMV, you may have a more probability of getting the motion sickness, because those non-driving tasks will make you lost the vision-based spatial awareness and prediction of your movement. So for those issues, our final goal is to make some methods to reduce the motion sickness during using the APMV. But before that, as a first step, we would like to understand the mechanism of the motion sickness and to make an evaluation method of it. Therefore, in this study, we focus on the modeling the motion sickness with a vision-based spatial awareness. So for motion sickness modeling, it has a long story. In 1978, Reason proposed a sensor conflict theory. He thought that the motion sickness is caused by the conflict between the sensor organ and internal motor in the brain. Moreover, in 1998, based on the sensor conflict theory, both proposed a subjective vertical conflict theory, which pointed out that the conflict of the motion sickness was from the vertical signals. In the same year, both proposed a first computational model of the motion sickness based on his SVC theory. This model have a one-dimensional acceleration inputs censored by the otoliths, and the output of this model is the motion sickness incidence, MSI. After that, in 2011, Rice saw the vision acceleration also affected on the motion sickness. So he proposed a 3DOF SVC model with a 3D vision inputs. Let's go back to the 2007. Kamiji and Professor Wada proposed the 6DOF SVC computational model of the motion sickness. In this work, they thought the motion perception of a human is not only from acceleration, but also from the angular velocity sensed by semicircular canals. In other words, they improved the prediction of motion sickness by modeling human vestibular system. Based on those related works, in this paper, we focus on the vision vertical because the passenger on the APMV may lose the spatial awareness, such as when they reading a book. Therefore, based on Kamiji's work, we propose a new computational SVC model with vertical sense by vestibular and visual interaction. Refer to human spatial awareness. The visual vertical can be thought to be derived from some cues, presumed to be parallel or perpendicular to vertical objects in the environment, such as buildings, trees, or the horizon. So, in this paper, we used a very simple and classical image processing method to estimate the visual vertical by extracting edge features of objects in the image and analyzing the direction of those edges. For example, this is an input image, what we see. Then, the edge features from the image could be extracted by the gradient method, just like this image. We can also compute the direction of each edges by using the arctangent function. After that, we made a histogram of the direction of edges. In the final, from the highest three frequent edge directions, we can estimate the visual vertical direction. After visual vertical estimation, we mapped the 2D visual vertical into a 3D space by the VISG block. This 3D space was assumed as the same space of vertical signal from vestibular system. Besides, we also assume that the VIG bar block maps the fused vertical G hat from vestibular vision interaction to the sensed visual vertical in the internal model. In other side, the predicted vertical G hat fused from vertical conflicts of vestibular system and visual system. Until here, this model can present the motion sickness caused by the vestibular vision interaction. To verify the accuracy of the proposed visual vertical estimation method, we did a static experiment at first. In this experiment, one participant sit on a stopped APMV and he wore a helmet. To measure the angle velocity and the acceleration of his head, as well as his eyes view, an IMU and a camera will sit on the helmet. Then the participant rotated his neck at the different angles. We recorded data when he held his head at those angles. Here, I would like to point out that the acceleration measured by the IMU equal to the gravity acceleration, because the APMV was stopped. Therefore, we can directly compare the estimated vision vertical with the gravitational acceleration. The comparational result was shown on the right side. In this graph, we can see that the coefficient of determination R² was 0.99, which means the estimated vision vertical had a strong linear relation with the gravitational acceleration, and they were also similar. Totally, the proposed method had a high accuracy of vision vertical estimation. However, Mikeson reported that the subjective visual vertical (SVV) of human usually had some errors when the rotation angles of the head become larger. So, how to model the motion sickness with those errors of human is still a future task. After the static experiment, we also did a driving experiment to investigate how the proposed 6DOF SVCVV model predicts the MSI, while the passenger riding the APMV with different visual conditions. So, we asked just one participant with the helmet and sit on the driving APMV, and this APMV was drove down a slalom path to simulate the avoidance behaviors in a shared space. We designed two vision conditions of using the APMV. The first condition we call the AD condition. The participant was asked to look forward during using the APMV. The second condition we call the RAD condition, which required the participant to read a book during using the APMV. So, we assume that the tendency of the motion sickness will increase when the participant reading the book. For the driving safety, actually we didn't use the autonomous driving system in this experiment, but we used the ghost driver method, which means the operator controls the APMV by using a remote controller. This video shows the vision vertical estimation during using the APMV with the AD condition. The top left image is the camera image, and the top right image is a corrected image by using the estimated vision vertical. And this video shows the vision vertical estimation in the RAD condition. We can see that the book blocked almost the background. The vision vertical was also estimated from the edge features of the book. In summary of results, this graph shows the estimated vision vertical by green lines and the gravitational acceleration by the red lines. We can see that in the two trials of AD condition, the estimated vision verticals were very similar to the gravitational accelerations in most of the time, except when the camera closed to the fence. Besides, in the two trials of the RAD conditions, in the most of the time, the estimated vision vertical were different to the gravitational accelerations because the book blocked the background. We copied those data 10 times and inputted them to the proposed 6DOF SVC-VV model, and the output of this model is the motion sickness incidence, MSI. Meanwhile, we also used the conventional 6DOF SVC model at the baseline. By using the conventional model without the vision vertical input, the first trials of the AD conditions got the highest MSI, but other trials got a very similar MSI. When we use the proposed method, which including the visual vertical inputs, the MSI of two trials of AD conditions were similar, but the MSI of the RAD conditions were higher than the AD condition. Based on those results, we found that the proposed 6DOF SVC-VV model can match the assumption of this experiment, which is the reading book during using the APMV, the passenger will lose the visual spatial awareness. In conclusion, this paper proposed a new motion sickness computational model considering the vertical sensor from vestibular vision interaction. A simple vision vertical estimation method was proposed by using edge extraction for view images. In the static experiment, the proposed method had a good performance of the vision vertical estimation. In the driving experiment, the proposed 6DOF SVC-VV model had a good performance of MSI prediction with different visual vertical conditions. In the future, we will design a large-scale subject experiment for this work. We also want to propose a new method to predict the 3D vision vertical from the image. The most important things of the proposed 6DOF SVC-VV model is the parameter optimizations. We also want to combine the vision acceleration and vision angular velocity into this model. Thank you for your attention. Thank you very much.